bosons. Thank you. Thank you for the introduction and the kind invitation to this very nice workshop. So this is a talk that is based on multiple works with many people, so some of which are in the room. Varun, my PhD student, Dorian, Hamid, Sev, Dhruva, Saeed, and Arsalan. And sort of before diving into the results of the computational power of bosons, I want to sort of give you a bit of motivation and context for why we care about these systems. So we heard a bit about bosonic systems yesterday, but let me get you a reminder. So this is sort of one-on-one physics that you can do with bosons. If you send two photons into a 50-50 beam splitter, they will bunch together. This is something that is known as the Ongu-Mandel effect. It dates back to 87 actually, and this is kind of a fundamental physics effect that has been sort of generalized and has become what I guess all of you know as boson sampling. So indeed these statistics, they lead to remarkable physics but also remarkable quantum information processing capabilities. So this is a very nice figure that I stole from this paper that tells you all the wonderful things you can do by playing with bosonic modes, especially in superconducting devices. And today, so I'll be mostly focusing on the quantum computation part. But yeah, you should also think that bosons and photons in particular are sort of essential just to link quantum nodes together. And this is one example of a, let's say, an artistic depiction of what a quantum internet could look like. You'd have nodes that are a quantum computer, and they're being related by photonic links. So these systems are, really crucial for quantum information processing. Okay, and with an eye towards quantum computing, these systems, they've also led to landmark quantum computational advantage experiments. And so here, this is the picture of a Gaussian boson sampling experiment performed by the USTC group in 2020. And okay, whether they managed to actually successfully demonstrate quantum advantage, I think is sort of an open question, but this is in any case a remarkable sort of feat of quantum information processing. And the last thing that I want to mention regarding motivation is that beyond just sort of trying to demonstrate quantum speedup using sampling problems, these architectures are actually super promising for realizing universal fault-tolerant quantum computers. You have many companies, of course this is slightly biased towards France, but this is a list of companies that are exploiting fundamentally bosonic systems to build universal quantum computers. And this is a figure that comes from this paper that demonstrated the first quantum error correction beyond break-even and fundamentally using bosonic error correcting code, which you will hear a bit more about in the next talk. Okay, now the thing that I'm super excited about, and I guess the journalists are also super excited about, is a recent work of Robert and collaborators, where they managed to factor or to derive a factoring algorithm that allows you to factor, let's say, n-bit integers in polynomial time using only constant space. Okay, and the thing that I want to emphasize, you'll see why this is important in the talk, is that there's no sort of crazy gate. The way that this algorithm works is really based on sort of state-of-the-art gates that you could realize in the lab. Of course, there's a catch, right? Like if you have n-bit integer that you want to factorize, you have to fit those n-bits somewhere as an input to your problem. And so if you only have constant space, well, you have to sort of pay a price in a different way. And the answer to that question, or the resolution to this problem, is energy. So this is sort of the subtitle of this journal article. Actually, I'm the one responsible for this. Sorry about that. So when they were sort of asking for expert opinion, I sort of jokingly said, oh, you know, this would require the energy of multiple stars. And then they loved it, and so they put it in the title. But okay, this is not a precise statement, but I think it sort of captures the point. And I think it motivates this question of, okay, if you start playing with energy in bosonic systems, then you can achieve seemingly crazy things, such as factoring in constant space. And so, yeah, this will be the theme of the rest of the talk. What's the role of energy in all of this? Okay, so this is what the next few minutes are going to look like. I'll give you the necessary background to understand what comes next. And then I'll sort of split the results that we've obtained in three, let's say, main themes. The first is energy growth in bosonic circuit. How do you actually come up with like high energy, let's say, even though you have a constant space? And then, okay, how can you sort of tame these computations? Like maybe if you allow crazy energy, you can solve problems that are a bit too complicated to be true, let's say. But maybe if you put reasonable restrictions on energy, there you can assess the computational power. So you can get upper bounds on the computational complexity. And conversely, you can also ask, okay, now, if I think of energy as a resource, as sort of a necessary ingredient to solve problems, can I get also lower bounds? Like if I allow more energy, can I solve more problems? Okay, so this is the typical depiction of a harmonic oscillator. So these are sort of discrete levels, and this goes on, so it's virtually infinite. The main difference with like the standard qubit paradigm is that the Hilbert space is infinite dimensional. So here is a countable basis, which you can think of a photon number basis if you're in photonics, or more generally particle number basis. And on this space, you have canonical operators that are known as position-like, momentum-like operators, and they satisfy this fundamental canonical commutation relation. And so this fact is sort of a reassuring fact in the sense that you can convince yourself, if you, let's say, take the trace of this expression, that there's no way of realizing this relation in any finite dimensional space. So the reason we are sort of working in infinite dimensions is not because we sort of love to do crazy math. Well, that's a bit part of this, but the true reason is that to actually describe the physics, we require this kind of mathematical background. And then the types of other operators that we'll use in what follows are there to define the concept of energy in this framework. So you define the number operator. So the number operator, if you look at this countable basis, has this basis as an eigenbasis. If you measure the number operator, it gives you back the number of particles in the system. And as a result, we define energy as this average particle number. Okay. So in the rest of the talk, when you hear energy, this is the definition. Okay, now if we turn to quantum computing, how do we compute in this infinite dimensional space? So this has been actually pioneered by Lloyd and Braunstein back in 1999. And what they did is to define a model of continuous variable quantum computation, because you're computing with these observables that have a continuous spectrum. And the typical type of Hamiltonians that they would allow in their framework are polynomial Hamiltonians. So anything that you can cook up by playing with position momentum operators. And just compared to the previous slide, these index, they just labeled the subsystems for which you define this position momentum. Okay, now you can use those polynomial Hamiltonians to cook up, let's say, standard gate set. So here's an example. You can notice two things here. So one is that each unitary operator here is being generated by a Hamiltonian that is indeed a polynomial in position momentum. And some of those are Gaussian, meaning the polynomial is quadratic. And some other are non-Gaussian. And okay, this means you're looking at a polynomial that has degree strictly more than 2. And if you come from a DV setting, discrete variable setting, you might think of Gaussians as loosely being sort of Clifford gates, and non-Gaussian gates as being non-Clifford gates. In particular, if I only have Gaussian operations, I can actually simulate a bosonic quantum computation efficiently, and you sort of need this non-Gaussian element to go beyond the classically simulable regime. Okay, and I want to emphasize two specific gates that are sort of part of this gate set. One is the Fourier gate, and again, you can think of this as sort of the equivalent of the Hadamard gate in this infinite dimensional setting. And the other is the cubic phase gate, which is this non-Gaussian gate over there. And again, okay, think of this as sort of the T gate. There's a way of making this precise, which uses essentially the GKP encoding, so a way of embedding discrete variables into continuous variables and infinite-dimensional Hilbert spaces, where indeed in the logical space, this gate sorts of play the role of a logical T gate, and that gate of a logical Hadamard gate. Okay, so given this background, let's see how we can make energy grow in bosonic circuits. So I want to present you with a fairly simple circuit. So we have a single system here. We start in the zero state. It's called the vacuum, the state of with no particles. And then we just alternate between a cubic gate, a Fourier gate, a cubic gate, a Fourier gate, and so on. Okay, so in the DV setting, this would be like, well, TH, TH, TH. Okay, now one thing that's different from the DV setting is that now the space is infinite dimensional, and as a result, this kind of circuit makes the energy grow. Okay, and it makes it so actually in a dramatic way. So one thing that we prove is that if you look at the average particle number of this output state after sort of T layers of this alternating gates, this is the sort of bound that you can show. And so what you should focus here on is this term. So you see that the average number of particles in the system actually scales doubly exponentially in the system size.
So you mean a medium-sized star is not enough?
Yes, exactly. This is where I'm going. So. Yeah, totally. And actually, so in your talk, you mentioned this this term of galactic algorithm, and I think this is a galactic algorithm. This is truly something that actually, if you sort of crunch in the numbers and you try to see, okay, what's the number of photons that I would need to, I don't know, like run this computation for depth 7 maybe, then this is sort of what you need, okay? So let's say all the photons radiated by all the stars, you know, in the Milky Way or something. Say what? Yeah. So yeah, so the point is like, okay, this feels very unreasonable. I'll also present you with more reasonable results in a second, but okay, this is just to emphasize what can go wrong. And this is, again, I mean, what's very important here is this is a standard gate set, right? This is what we use in the literature, in papers about, you know, doing quantum computing in bosonic systems. So, okay. Yeah. So in this case, actually, they don't change energy. And well, this brings me to maybe giving you the intuition for what this happens. So indeed, this gate here, the Fourier gate, is a Gaussian gate. And what it does is just exchange Q and P, right? So it doesn't change energy, indeed. And there's this kind of amplification effect, because what the cubic gate does, like in the Heisenberg picture, if you see the evolution of position momentum, it doesn't, it's kind of a function of Q, so it doesn't change Q. But for P, it maps P to P plus gamma Q squared. And now you can see what sort of happens as you progress in this circuit. So P will get amplified to P plus gamma Q squared. Then the Q squared will become a P squared. Then the P squared will be amplified again to P squared squared, and so on. And so you get this kind of repeated squaring effect that in the end actually leads to these kind of lower bounds. Okay, but it gets worse. So here are other weird facts about energy growth. Yes, so I showed you an example where the energy grows doubly exponentially. Actually, we can cook up other polynomial Hamiltonians that are sort of well-defined, but where the energy diverges arbitrarily fast. So we can do, we can do towers of exponential of energy, let's say exponential of exponential of exponential of t in time t. Okay, we can do worse. For some polynomial Hamiltonians, again, well-defined sort of gates, the energy is always infinite. So it means if I look at the unitary gate exponential ith, for any strictly positive t, the state has infinite energy directly. It gets worse. Right, so you could ask, okay, but maybe, you know, if I give you a computation, maybe I can actually rule out, right, that this kind of crazy behavior happens. Okay, this is where things get, yeah, a bit terrible, which is, if I give you sort of a computation that is based on polynomial Hamiltonians, it's actually an undecidable problem to say whether it will reach infinite energy or not. Okay, of course, this is kind of a worst case result, and you could expect, and this is what we're going to see, that for like specific gate sets, you can say stuff, but yes, but this is kind of a striking fact, and the way this is proven is by making a reduction to the undecidability of Diophantine equations. Okay, so this is about energy growth, and these are sort of crazy results that tell you that we're doing essentially nonsense in quantum computing in the bosonic regime. So I want to give you maybe now a different message, which is to say we can still sort of tame these computations. And so the first thing is, I think, the result that you should expect, which is if I give you the promise that I have some bosonic computation, and now I give you the promise that the energy stays polynomially bounded throughout the computation, then you can actually show that you can simulate whatever happens in BQP. Okay, so you won't get like kind of crazy, beyond the halting problem or these kind of things. Okay, but then you could say maybe this is not fully satisfactory. Like what happens if the energy is allowed to grow a bit more? So another thing that we prove is that if now you only require that the energy is exponentially bounded. So here, when I say polynomially exponentially, I mean in the size of the computation. And so now, in this case, we analyze specifically the case of the previous slide, so Gaussian and cubic phase gates. And then we get a PP upper bound on this computational model. And finally, you could say, okay, if the energy is bounded, but I don't know the bound, what happens? And there we show that the computation that you get is still decidable. Okay, so here we're just assuming that, okay, somehow the energy throughout the computation kind of can go completely crazy, but it never sort of reaches infinite. Actually, we require a technical sort of condition that is slightly stronger than this. But the intuition is this, that, okay, if the energy doesn't get to infinity, even if you don't actually know like how high it will go, you don't solve the halting problem, essentially.
By uniformly, you mean uniformly over the course of the computation?
Yes.
While the bounded depends on the input parameters, I guess.
Yeah, absolutely, yeah. Right, so let me maybe quickly focus on this result. So how do we actually achieve this this is essentially a classical simulation algorithm, right, in PP. So this is the setup a bit more precisely. We're looking at bosonic circuits that are based on Gaussian gates and cubic phase gates, which are the same ones that can grow this energy doubly exponentially that we just saw before. We fix the input to be the vacuum state, and at the end of the computation, to get some results, we make a particle number measurement on one of the subsystems. Okay, and actually the way we came to prove this results is in a series of work. So when we sort of first looked at this problem, we did a brute force approach to, okay, what if I just bound the energy and try to do cutoff in the Fock basis? What do I get? So we got this sort of naive exp space algorithm. Then we refined it using an idea that you can think of as sort of a bosonic version of stabilizer decompositions, where you're essentially reducing the complexity of a state by writing it as a superposition of simpler states. And in a work that is to come, we are putting it down to PP, and here the idea is that we are sort of recompiling these computations that use Gaussian plus cubic circuits into computations where you put all the non-Gaussianity at the beginning, and then all the rest is Gaussian. And this is very similar to what you would do in the qubit setting with magic state injection, right? You can pull all the non-Clifford resources, put it at the beginning, and then all the rest is Clifford. Okay. Right, so this was about upper bounds, and now we want to understand lower bounds. I said that energy can be thought of as a resource for solving problems, but let me say what I mean by this. So a first result that we show is that if you're using gates that are based on polynomial Hamiltonians, you can actually solve NP-complete problems and actually NP-hard problems using constant space and exponential energy. Okay, so this is actually very similar to the setting that was studied by Robert and his collaborators, but we're working with like a different gate set, like purely bosonic, and so this happens. Actually, if you use exponential energy, you can, in these models, you can solve NP problems. Okay, and naturally you want to ask, okay, and now if I keep increasing the energy, what happens? And so what happens is sort of what you would expect in the sense that if now you're using kind of energy that is bounded by, let's say, a tower of exponentials, so this notation here with a k just means you're taking exponential of exponential of, okay. As we saw, you don't need k to be very large to reach the energy of the universe, but this is kind of just fundamentally, putting a message, let's say. And so this is what you can show. You can show that if you remain close to states that have this kind of crazy energy dependence, then you can solve problems in this class, so meaning problems that you can solve with a non-deterministic Turing machine in this time that is also this tower of exponentials. So the more energy you put in, the more, the harder the problems that you can solve get. Okay, and here again, the intuition is relating all of this to Diophantine equation, and there's actually sort of a very nice fact that I was not aware before this project, which is, so solving Diophantine equation is undecidable, but if you start sort of asking for, is there a solution of a Diophantine equation in this certain range, then you actually get this very nice hierarchy of complexity, which is essentially what lets us kind of get this energy hierarchy theorem. Okay, and maybe to give you an intuition, I said we're sort of relating or reducing to solving Diophantine equation. There's actually a very natural way of doing this, which actually dates back to early days of quantum mechanics. This was already noticed, I think, in maybe 2003, where if I want to, think about the integer solution to a polynomial system of equations, I can sort of equivalently think of this as asking questions about the ground state of a Hamiltonian that's a polynomial in the number operators of each subsystem, and those number operators themselves are polynomial in Q and P, so this construction gives you polynomial Hamiltonians. Yeah?
So do you know whether this is also true for the gates that we use, because we don't use this higher order?
I don't know. I don't know. It's an interesting question, yeah. Okay, so I think with this I can conclude with a few take-home messages. So maybe the first thing that I want to emphasize is that so the work of Robert and others, and also their very recent work, it shows that you can actually trade space for energy when you're doing computations, quantum computations, and you can think of sort of some of the results I presented as showing that you can also do this with time. So you can really trade time for energy in terms of computational resource. And so here the message is that when you're playing in these infinite dimensional Hilbert spaces, it's not enough to just say, okay, my algorithm runs in this time, this space. You also have to somehow specify the energy budget. And the other message maybe that I want to tell is that the other types of results that I showed you, they tell you that you can see dramatic energy growth in bosonic systems with like purely standard gate sets. And I think this calls for sort of sitting down and revising those models, like thinking, okay, what's actually a good model? So this essentially brings me to my first open question, which is, okay, what is such a good model? There's sort of many ways that you could go about this. One way is to say, well, I'm fine with just putting this kind of energy promise on my computation. Okay, I don't think this is kind of the nicest way of doing it. It will sort of work out for practical applications, but it feels also a bit unreasonable because you no longer get this kind of circuit model where you're free to apply any gates. It means in an algorithm, I have to check, oh, if I apply a new gate, do I violate this energy constraint or do I not violate? It's kind of not so clear what you can do with these models. And another sort of idea that is coming from Saeed, one of my collaborators, is that, oh, you could think of a model where you actually allow the energy to sort of blow up throughout the computation, but as long as you don't measure, right? So the model there would be something like, okay, I have this detector. If it measures something of exponential energy, will blow up. But as long as, by the end of the computation, the energy has kind of decreased, then the detector is not going to blow up. And so you could potentially think of this as like, yeah, we're sort of, putting ourselves in superposition with a state where we're using crazy energy. As long as we don't look in the box, we're fine. And then the energy sort of goes down. What's the computational part of this? Of course, this is less on the practical side, but I think that this is a fairly interesting question. Kind of what are the limits of nature in this sense? Right, and I guess kind of a related question is, so we've already challenged the Church-Turing thesis, which is the thing that tells you that kind of any reasonable problem that you can solve efficiently on a Turing machine. So now this is sort of shifted to quantum Turing machine. And I think these kind of studies, they beg the question, should we shift a tiny bit again? Like, can we hope to solve things that are a bit beyond BQP? Or are all the things that go beyond BQP actually unreasonable from a physical standpoint? And the last thing that, okay, I didn't have the time to touch upon, but one of the things that we realize as well is that because of these kind of energy behaviors, you realize that the different gate sets, they have different ways of amplifying energy, and as a result, they don't seem to be computationally equivalent. Okay, and so more generally, this sort of opened these questions of, yeah, is computational power in fact hardware dependent? This is also kind of challenging the church-ring thesis. Yeah, can we hope to, just think about some infinite-dimensional quantum Turing machine and be safe with it? Okay, so with this, I thank you for your attention.
Yeah, thank you so much for the presentation. So I'm asking myself whether what you do is really quantum computation or whether you just use that energy and time are complementary. So my question is, what is the complexity of simulating classical Hamiltonian dynamics if you have third order, like cubic Hamiltonian functions? Is it maybe also PP? And is it then maybe not actually quantum?
Yeah, that is a good question. So, okay, I would say what we do is quantum, maybe not all of the results, but for instance, so one of the results that I showed was the fact that if you bound the energy throughout the computation to be some polynomial, then you get into BQP. But we have explicit models that satisfy this energy dependence and actually achieve BQP complete computations. So this is not something you'd expect kind of classically, like you have to do some quantumness there. But then to your question, I don't have a precise answer. Right? And I think it would be interesting indeed to say kind of, yeah, which part of this is fully quantum and which part of this is just, or we're playing with infinite dimensional or maybe continuous models of classical computation. Yeah, that's a great question.
Yeah, thanks for the very nice talk. I was curious if there's any, if you have thought about whether some of this can survive error and fault tolerance, that if there's like a fault tolerant model of bosonic computation that also has these properties that you suggest here.
Yes, so I think the answer is going to be no. I've not thought like too deeply about it. It's kind of one of the future, let's say, projects, but indeed, and I mean, here something sort of feels wrong, right? You have these exponential levels, and in order to run the computation, you'd have to carefully control all of these levels at the same time. This feels sort of unreasonable. But I guess the message here is more to say, these are the models that we've been using so far, and something feels fundamentally wrong about it. But yes, so my expectation is no, it wouldn't survive, yeah.
Thank you for a nice talk. I have just quick clarifying questions. So you had those different, yeah, like depending on the energy bounds in your computation, you land in different complexity classes. So how much it depends on specific gate sets that you use. So it can be like any Gaussian, okay, Gaussian plus cubic.
So you mean,
okay, what if you have some other?
Yeah, so for instance, for these, we're actually sort of cooking up the Hamiltonians in a very precise way to actually achieve this.
So in the model, so you can sort of by
exactly. So the limitation of the model is this. So we can play with polynomial Hamiltonians. It's a bit more technical than this because we want them to define like proper unitary evolution. So we have to put a bit of constraints there. But okay, the general idea is that, yeah, we play with polynomial Hamiltonians. This is our constraint. This is the model. And using this, what can we do? And so indeed, for instance, Gaussian plus cubic, they allow you to grow energy quite fast. But in that model, we don't show that you can solve NP. So to solve NP, we need to do a precise construction based on specific polynomial Hamiltonians. Yeah.
Okay, so you need to precisely implement other polynomials. You
yes,
cannot rely
exactly.
on approximations as in the original paper.
Exactly. Right? No, but so, yeah, and so this is actually a fully open question which relates to the question of hardware dependence, which is how do you connect those models together? Because, so in the original paper, there's sort of this argument that, use Trotter bounds and everything's going to be fine. But these Trotter bounds, they're just not valid for unbounded operators. And they're probably actually wrong in this setting. So, yeah.
Thanks.
All right, let's thank Ulysse again.
Thank you.